afternoon section. The first speaker of this section is the Marcelo França. Talk about entanglement and steady-state entanglement beyond thermal limits. Marcelo, just 30 minutes, okay?
50? Cool. Thanks, man. Okay, fine. So, thank you guys for inviting me here. Let me start again my clock. And so I'd like to thank the organizers for having me here. Good afternoon, everybody. I hope you've had a nice lunch. And so I welcome you guys to listen a little bit about something different from what we've heard this morning. I'm going to talk about a little bit of quantum optics adapted to understand quantum thermodynamics. So quantum optics, quantum open systems, and quantum thermal is the overlap of these three areas that I'll discuss today. And so I'll basically talk about how to achieve more entanglement in kind of steady-state dynamics, more compared to what people have already achieved with thermal limits. And so basically, the idea is that we're going to discuss thermal engines, or similar to thermal engines. And classically, when we talk about thermal engines, we are discussing basically incoherent exchange of energy. We call it heat. And basically what we can get with it is work, which is kind of coherent energy, or we can also get coherence in the sense that we can get coherent signals transmitted and codified and so on. And the question is, what can we do if we go to quantum engines? Well, everything is quantum, but what I mean is that when we start to exploit quantum properties of your engine, right? So in this case, the analysis, the thermodynamic analysis of heat in quantum engines is very old. For example, you find Steve is kind of forcing his eyes. I apologize for the size of the letter, but for example, as soon as masers and lasers came around, you also had thermodynamic analysis of the systems, and in this case, we are talking about using incoherent exchange of heat to produce for semi-classical coherence. You can also use incoherent exchange of heat, so incoherent exchange of energy or heat to produce quantum coherence. For example, that's what you get for Bose-Einstein condensation. You use heat exchange to cool down your atoms all the way to a situation in which they behave collectively in a quantum coherent way. And for example, you can also use heat to produce entanglement. And this is what I'm going to focus on. And if we're talking about producing entanglement, basically we are thinking about a global system made of different parts. And from now on, I'm going to talk about qubits, and in particular about 2 qubits, okay? Just to simplify. So I'm talking about a heat exchange that produces entanglement in 2 qubits. And to produce entanglement, you need somehow to act globally on these guys. And one alternative, for example, coherently act on the qubits from outside, so you can externally drive them at the same time, or you can prepare them in a particular initial state and then allow them to interact with your bath to exchange heat. This is basically what these papers do, and this is only a small sample of the vast literature on the subject, okay? There's a very large literature on the subject. You can also embed your coherence in the internal structure of your qubits, in the internal dynamics of them, or, for example, you can erase which qubit information. And that's what these do. For example, you can couple the qubits while you allow each one of them to interact with reservoirs, independent reservoirs, but because they are coupled, the dynamics can eventually produce a steady-state entanglement. You can also, for example, put them under the action of common baths, and in this case, you erase which qubit information, and again, the steady state can have some entanglement, or you can do both of them. And again, this is a small sample of a vast literature, okay? However, and this continues the sample, no matter what you do, if what you do is to couple your qubits to thermal baths. There is a limit on how much entanglement you can produce. And this limit has already been calculated, and the limit is 1/3 of coherence. If all that you're doing is coupling your systems to external baths at different temperatures, okay? And we have to remember also that because they are thermal baths that you are coupling your systems to, the reason for this limit is that because you're coupling to thermal baths, there's always decoherence, unavoidable decoherence happening in the system. And that's the reason why you cannot go much. So if you want to go beyond, you have to do some feedback. For example, you have to be feedback information into your system, or you have to do some filtering, in which case you throw away part of your realization. And you can also actively change your environment, or in which case you can even do quantum computation, or you can passively measure the environment. Again, you can do quantum computation by doing this. But the fact is that if you want to go, in general, if you want to go beyond the 1/3 limit, you have to do something else extra to your system. So now the question that we asked ourselves was, is it possible to go beyond the 1/3 limit in the same framework, dynamical framework? And that's what we did in this work, and that's what I want to tell you guys from now on. So basically, the dynamics of the qubits is going to be the same, basically, as if it were interacting with two thermal baths. Same type of dynamics. It's just that we switch one of the baths into negative temperature. And by switching one of the baths into negative temperature, we can actually produce more steady state entanglement than if they are just bona fide thermal baths. I'm going to tell you guys why. So this is the first part of my talk. The second part is that the steady state of your system is going to be out of equilibrium. So basically, you're going to keep producing entropy because you're sustaining a state that is out of equilibrium. The question is, by going to more entanglement, do we produce more or entropy or not? So that's another question that we answered. And then third, we show how to do this in the lab. Okay, so that's the outline of the talk. So the first part is we're going to borrow the same level structure from a previous paper. So in this work here, in this work here, basically they exploited another very nice, neat property of quantum systems. So if you have a classical engine, you couple it to a hot bath, a cold bath, energy goes through it, you do some work and so on and so forth, right? But if you have a quantum system, you can do something interesting, something neat, something cool, well, cool and hot, which is you can actually interact part of your Hilbert space with a cold bath and another part of it with a hot bath. In this case, for example, what this paper does is it analyzes the situation in which the antisymmetric transition of your two qubits is coupled to a hot bath, and the symmetric transition is coupled to a cold bath. Well, so before going there, just to remind you guys that if you have two qubits, you have this diamond structure. This is the ground state, both qubits down. This is the upper state, both qubits up. And this is the one excitation subspace where you either have the antisymmetric superposition of them and the symmetric superposition of them. And what is analyzed in this paper, and it's the basis of what we did, is the situation in which the bare Hamiltonian of your guys is that they are uncoupled, but they follow a dynamics that is open system dynamics, Markovian dynamics, in which you have two baths acting on them, but one of them acts on the symmetric part and another one in the antisymmetric part. These rates here are the rates at which you have the dagger and the raising and the lowering operators, joint operators. And basically temperature is defined by the ratio between these two rates. And as long as this plus rate is smaller than the minus rate, you have positive temperature. Okay? So that's what they analyzed, and they showed that the limit here is when this guy goes to infinite temperature, this goes to 0 temperature, and you end up with 1/3 of entanglement. I'm going to explain why very soon. So that's what I just said. If this is smaller or equal to this, you have positive temperatures. And so what happens if you have infinite temperature in the hot bath and 0 temperature in the cold bath is that your steady state is a mixture of the ground state and the antisymmetric state, which has 1/3 of entanglement. This is not difficult to understand. This transition is at infinite temperature, which means that the chance to go up is the same as the chance of going down here. This transition is 0 temperature, which means that the chance of going down, there is a chance of going down and 0 chance to go up in this transition, right? That's the limit. So basically, if you go up from here, you can either come down here or you can come up here. And as long as this rate of going down is much larger than this rate of going down, you actually, as soon as you come up here, you go down here, here, and come back. So there are two ways of coming back here, which is this way and this way, going around, and only one way to come up here. And the best situation that you get is when you end up with twice the population in the ground state than you have in this excited state, and these two guys are empty, and that gives you 1/3 of entanglement. Okay? So what we did was, okay, can we go beyond? And the answer is yes. When you turn this temperature into negative, and what does negative temperature mean? Okay, negative temperature means basically when you couple this guy to an incoherent reservoir, one that exchanges energy with the qubit incoherently, but the chance to go up is larger than the chance to come down. That is equivalent to negative temperature. Okay? If you do this, then basically the best situation here is achieved when this cycle becomes, so if you do the left cycle going right and left, you actually end up being pumped here. So you reach an equal mixture of being down and being here. You can never get rid of this guy because there is always a chance of coming down from both sides, okay? Fine. And this picture here, so is a kind of phase diagram. This region here is when you have both temperatures positive. This region here is when you have both temperature negatives. And this is actually a copy of this region. Basically, the reason being because if you have both temperatures negative, you just redefine your qubits. It's just whatever was G, you call it E, and you are in kind of an inverse situation here, right? So from the perspective of building entanglement, it's the same. But what is nice is when you have here this anti-diagonal here, because this one, or this diagonal, sorry. This one is kind of, you have inversed only part of your Hilbert space, so you make a kind of twisted situation, right? And you get negative temperature on one side and positive temperature on the other side. And that's why you get this improved entanglement. So the next question is, how does the entropy production go? So if you only have positive temperatures, okay, the dynamics is that of qubits interacting with thermal reservoirs. And if you consider the whole stuff, qubits and reservoirs, the qubits are in a steady state, so the state of the qubits doesn't change. So there is no change in the entropy of the state of the qubits. And basically what's happening is that you have energy flux through the qubits to keep the steady state. And basically the rate of change of entropy is due to the baths. And that's what you get here, sorry. That's what you get here. If you quantify the flux of heat for each reservoir as the trace of the bare Hamiltonian times the respective superoperator acting on the steady state, then the rate at which you produce entropy, the rate at which you produce irreversibility in your system, is just the sum of the entropy changes in the bath. And you have to remember that the state of the system doesn't change, which means that the flux of heat from one reservoir plus the flux of heat from the other is equal to 0. So the question is, what happens if you have a negative temperature reservoir? Well, if it's a negative temperature reservoir, it's not given for you that you can think about it as a bona fide reservoir. But even in this situation, there is a way to quantify, to calculate the entropy production rate. And this has been developed through a large number of papers. This is, again, a sample of them. And what you do is you borrow the same idea of Crookes to calculate production of entropy and so on. That is, you calculate the entropy for each trajectory of your system, and you calculate kind of the entropy of coming back. And then for each trajectory, you define an entropy associated to that particular trajectory. So how much irreversible is that particular trajectory? That done by Crookes for classical thermodynamics. So these guys expanded it for the quantum thermodynamics, in which what you do is do the same for quantum trajectories. And the calculations follow. So I'm not going to explain quantum trajectories here, but very shortly, if you have your baths, you can decompose the dynamics into a cross map, cross decomposition. And one given trajectory of your system is basically given by a sequence of cross operators acting on a system that will drag a pure state into another pure state. And there is a probability associated to this sequence. And if you are able to define what would be the backwards evolution in respect to that sequence, then you can calculate the probability of that backwards evolution, and you can define the variation of the entropy in that particular trajectory by just calculating the log of the ratio of these two probabilities. Okay, and then if you do this, the entropy production rate for a sum of probabilities, for the average of these probabilities, is just you average the rate, the change of entropy of each trajectory, and you divide by a given amount of time, and this gives you the rate. You have to remember that we are talking about steady state, and you guys are going to say something like that. Yeah, but if it's steady state, your state doesn't change. So what do you mean by? But then you have to remember that now I am in the quantum trajectory scenario, which means like this. I have a particular state. It's interacting with your bath. And in each time step, small time step, what I'm doing is that I'm measuring the bath and finding out if the bath has gained or lost, energy. And then, basically, my state is going to change because I'm measuring the bath, and the bath is interacting with the system. So I'm indirectly interacting with the system. I'm indirectly measuring the system. So now I'm going to have a change of states in the system. But then if I average over all the possible trajectories, I'm going to find out that this average doesn't change because it's the solution of a master equation that actually is already in the steady state. But I can calculate the entropy variation for each trajectory, and the average of this variation over each trajectory gives me the entropy production rate. Okay? That's the idea. And you guys see that as soon as I go negative, the entropy production rate increases. And increases significantly. Which means that, yes, I can produce more entanglement, but actually I'm kind of driving my system even more out of equilibrium. Okay? And to sustain this entanglement, I need to keep producing more entropy. Cool. But the interesting thing is that because of the type of dynamics that we have, in fact, we could have used the same equations as before, as if the system were interacting with positive temperature reservoirs. That's particular to the fact that we have a particular way of interact with the baths and a particular dynamics. Okay? If you go to the quantum trajectories scenario, it's very easy to understand this, because basically you have the same cross decomposition. All that is changing is just the rates, just the probabilities of going up and down. But the overall type of trajectory that it can produce is still the same. So it's reasonable to imagine that things should not change that much. So the last part of the talk is, how do you do it in the lab? Okay? So the goal is to achieve a situation in which the symmetric cycle has one dynamics and the antisymmetric cycle has another dynamics. So one way to do this in the lab, we've borrowed ideas from an old paper of ours from 2011, in which we came up with the following scenario. Pick up two qubits that interact with the same mode of a leaky cavity, and each qubit is incoherently pumped and can decay spontaneously. So these two guys here, they form independent baths acting on each qubit, okay? And together they produce you one equivalent thermal bath acting on each qubit. But then they also couple to the cavity, and the cavity can leak. So the total Hamiltonian of the system is this one, and this is particularly chosen in such a way that the coupling to the cavity is done through the symmetric subspace. This has to do with the dielectric orientation of my qubits and so on, okay? But still, this you can choose this. And then obviously, symmetric or antisymmetric is just a choice, okay? I could switch the phases and everything would hold. So the entire time evolution of my system is given by, again, a master equation in which you have the incoherent pump of each qubit, the spontaneous decay of each qubit, and the decay of the cavity. However, if the decay of the cavity becomes larger than the coupling of the qubits with the cavity, we can adiabatically eliminate the cavity. So the cavity will only work as a Purcell effect on the decay rate of my qubits, but as soon as an excitation goes into the cavity, it leaks. So it never comes back. So you never get Rabi oscillations. Okay, so the effect of the cavity is just to enhance the decay of the system. But then because of the symmetric coupling, it will only enhance the decay of the symmetric subspace. Therefore, the temperature, the effective temperature associated with each subspace is going to be different. Because the symmetric will have this extra Purcell effect, while the antisymmetric won't. Well, so here we've tested the full model with a adiabatic elimination versus the numerics of the, without the adiabatic elimination versus the adiabatically eliminated. And you see that as soon as kappa is larger than G, basically the two models coincide. So this is the range of parameters in which our physics maps the physics that was brought from the previous paper for thermal analysis. Okay, this is the range of parameters that we're interested in, and here what we show is again the incoherent pump as a function of the coupling constant to the cavity, the decay of the cavity as the function of the coupling constant, and what you guys are seeing here is this for two different spontaneous emission rates. And this is the limit of the positive temperature. So down in this region here, you have positive temperatures. In this region, you don't. So for two different spontaneous emission rates. And so if pumping is smaller than the spontaneous emission, you have two positive temperatures. And you see that you are very limited in the amount of entanglement, and the best that you can do is basically reach the 1/3 limit, which is given by this red dot dashed curve here. Now, if the pumping rate is larger than the spontaneous emission, then you can go to negative temperatures, okay? And then there are two regimes. One in which this rate is larger than spontaneous emission, but the Purcell effect is still important, so you have negative temperature on one side and positive temperature on the other side, and that's where you get the best entanglement. The other cases in which the cavity decay is so large that you are out of the strong coupling regime, there is basically no Purcell effect anymore, and then if px is larger than gamma, both goes into negative temperature, and you cannot produce that much entanglement anymore because you've just redefined G and E. So it's back to positive temperatures with redefined guys. So if you are an experimentalist in the audience, that's what you want to do. You want to have a spontaneous emission smaller than incoherent pulp, that is then smaller than the coupling of the atoms with the cavity, that is then smaller than the decay rate of the cavity, but you also want to have that the overall Purcell effect to be larger than the incoherent decay rate. So that's the take-home message for experimentalists. And finally, what I wanted to say is that we also tested the robustness of our scheme against other sources of decoherence. For example, we included in the dynamics dephasing, individual dephasing of the qubits. We included different detunings to the cavity mode, so if the coupling is not perfect with the cavity mode, it's not resonant. And we also included temperature in the decay rate of the cavity. So the cavity is not decaying to the vacuum, it's decaying to some temperature, so there are thermal photons involved. And you see that in the three cases, the scheme is quite robust. Obviously, in some cases, more robust than in the others, but the scheme can sustain at least a little bit of other sources of decoherence without losing the steady state entanglement. And so amazingly, I managed to give the talk in time, which probably means that I have missed lots of important information. So in the questions, in a couple of seconds, you guys are required to remind me of the important information that I forgot to tell you guys, okay? So the conclusion is that, yes, you can get more steady-state entanglement as long as you go negative in the temperature. But the price that you pay is that you produce more entropy, and the scheme is feasible and robust in the lab in different setups. And just to finish, these are the usual or not so usual suspects of this work. This is part of a long-term collaboration, like more than 10 years, with Alexia and Dario. And Francesco is Dario's PhD student. Actually, he did all the calculations, right? We just enjoy presenting. So thank you very much.